Well, good morning, and my name's David Brenner, and I am the director of the Center for Radiological Research and also the director of our RARAF facility where you're at right now. So my job is to give you an introductory lecture on why we're interested in microbeams in the first place. So why microbeams is my title. So, well, I think we all know this, but what a microbeam can do is deposit ionizing radiation damage in small microscopic or submicroscopic, subnuclear regions of cells. And what I'm going to demonstrate to you, I hope, is that this allows investigations of single particle effects of a single, shall we say, alpha particle or proton. And it also allows us to investigate both intra and intercellular mechanisms of stress response, how damage transmits itself from one location to another. So we'll be interested in situations where we irradiate a single cell nucleus, where we irradiate a single cell cytoplasm, where we irradiate specific parts of a cell, and where we irradiate a cell but guarantee that the neighborhood cell, the neighboring cell, is not irradiated. So those are four of the common situations that I'll talk about. So let me actually delve a little bit into history of why we, and others too, first started thinking about microbeams. Certainly in our case it was for the issue of radon, and radon, as you know, is one of the big players, the biggest source of naturally occurring radiation exposure that we have, naturally occurring radioactive gas that ultimately deposits energy through alpha particles. And it has a long and interesting history, which I won't go into now, but here's a 16th century woodcut of a miner being treated for what we now believe to be lung cancer. So here's the story. This is why we're interested in microbeams. So what's plotted here is for different populations, and we'll start with miners, Colorado miners, uranium miners. We're going to look at the number of traversals of target cells. In the case of miners, it would be the basal cells in the lung. So how many cells get no traversals? Well, this is actually in a year of a typical Colorado miner. This number. How many get one? How many get two? How many get three? How many get multiple traversals? So you see the story with the Colorado miners is that most of the target cells in the bronchial epithelium get multiple traversals. Now let's compare that with actually what we're interested in, which is domestic radon exposure, where the average doses, of course, are a lot less. And here, what we have among the 100 million basal cells in our lung, almost all of them over a, shall we say, year, will get no traversals at all. A few of them will get one traversal, and it will actually be very rare for an average individual to get any cell with multiple traversals. So you can see that what we're really interested in, if we're interested in the risks from domestic radon exposure, are the effects of a single alpha particle traversal. And that, of course, you can't directly get from the Colorado miners, because you will never get a Colorado miner where most of the cells have single alpha particle traversals. And let's compare that also with a conventional in vitro experiment, where, for example, we irradiate some cells in a dish and we give, on average, one alpha particle going through every cell. But that's on average, of course, and if you do a broad beam irradiation, you'll get a Poisson distribution in the number of hits per cell. So, for example, in 100,000 cells, 37,000 will get no hits, 37,000 will get one hit, and a significant number will get more than one hit. So again, if this is our goal, to figure out what are the effects of exactly one alpha particle, it's tough to get that from the Colorado miners, but it's also tough to get that from a conventional in vitro experiment, because you are always having to battle the Poisson distribution. So you'll end up with multiple traversals that you don't really want to know about, and you'll somehow have to unfold this information to get the effects of a single alpha particle. Now the elegant way around that is indeed the microbeam, where you can do a conventional in vitro experiment, but now instead of being dominated by the Poisson distribution, you can tell the system to give a single alpha particle, shall we say, to every cell. So you can mimic a situation like domestic radon exposure. So that was actually our original motivation here at Columbia for wanting to build a microbeam, but its uses, as we'll see, have expanded greatly since then. And here, for example, is one of our early microbeam studies where we're looking at oncogenic transformation, in vitro oncogenic transformation. And here is a control population of cells. Here we've put exactly one alpha particle through a group of cells, and this is the transformation frequency. And that was done with the microbeam. Compare that with the Poisson distribution. Again, here's the control numbers. And here's where we put a mean of one alpha particle through a group of cells. So some get 0, some get 1, some get 2. And what you see is there is a difference between putting exactly one alpha particle through a cell and putting a mean of one alpha particle through a cell. So again, that gives you some indication of the power of a microbeam to be able to simulate real-life situations. So let me carry on with why microbeams. I've talked about investigation of single particle effects, but one of the big uses these days is to investigate intra and intercellular mechanisms of stress response. And I'll give you a few examples there. This is from Tom Hayes' work, where what we're doing in this experiment is irradiating cytoplasm only. We want to guarantee that we'll not hit a nucleus. So here are some cells that have been imaged, and the computer has figured out where the nucleus is and is giving orders to the microbeam, don't irradiate the nucleus. So the microbeam is hitting the cell here, 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 here. So in all cases, hitting the cytoplasm, but not irradiating the nucleus at all. And again, that's something that you can't do in any direct way without a microbeam. And again, let's look at intercellular responses. And the classic example then is the so-called bystander effect, bystander response. And I'm sure most of you have come across what the bystander effect is. But the general idea is that damage is expressed in cells which are near to an irradiated cell, but they themselves have not actually received any energy deposition. So, to give you a little graphic example here, imagine that we can irradiate just this one cell out of this group of blue cells. You'd certainly expect effects in that irradiated cell, and indeed you see those, but in fact you also see effects in these so-called bystander effects, bystander cells, which themselves have not been irradiated, because with the microbeam we can guarantee that only this cell was irradiated and these were not. And yet we see effects in the hit cell and also in neighborhood bystander cells. So that's the so-called bystander effect. And since the bystander effect was first reported by Jack Little well more than a decade ago now, it's been seen in a variety of different endpoints. Really, all the endpoints that we have in our field, in biology, in radiation biology, wherever we can actually measure, we are seeing these bystander effects. So somehow information is being communicated from hit cells to neighboring non-hit cells. And as you can imagine, the the microbeam is a great tool for investigating bystander effects, because you can hit cells, but you can also guarantee that you won't hit neighboring cells. So we're interested in this for a couple of reasons. One is that it's telling us a lot about the basic mechanisms of how damaged signals get transduced from one location to another within a cell, between cells. But it's also of practical interest in the field of low-dose risk estimation, which is of great interest in our center and societally, of course. And let me give you an example of the sorts of things I mean in terms of low-dose risk estimation. So here's a study from the Tom Hay group done here at Columbia, where they're looking at induced mutants per surviving cell, and what they're doing is irradiating a larger and larger proportion of the cells on the dish with exactly one alpha particle. So here, 100%, every cell on the dish, 100% of the cells on the dish is being given exactly one alpha particle. Here, 20% of the cells on the dish are being given one alpha particle, and 80% are not being hit at all, and likewise 10%, 5% here. And you see this interesting shape of, in terms of a dose response, which is really quite interesting, that you get the same effect whether you irradiate 20% of the cells or 100% of the cells, which is really quite extraordinary. But you see the shape of this dose response curve, which is basically saturating. It's downwardly curving, and as you go up in overall dose, you get smaller and smaller increases in risk. So, but if you picture what the if you'd only had this measurement and you wanted to extrapolate to lower doses, well, you'd surely do this. You'd surely extrapolate a linear response to lower doses. If you did that, what you could see is you would actually underestimate the risk at these very low doses. So this is a case where the linear model, a linear extrapolation from high doses to low doses, would actually underestimate the low dose risk. And of course, one of the big issues is, well, is this a general phenomenon? Is this true in general, that if we use a linear model to extrapolate from low doses to very low doses, are we really going to underestimate the risk? And various people, since the bystander effect was first talked about, have used a variety of different techniques to look at bystander studies. The first one, the Jack Little approach, was to irradiate with a broad beam of alpha particles, but at a very low dose, so that most of the cells actually aren't hit at all. But of course, you don't know then which cells are hit and which cells are not hit. So that's where the first studies were done, but it's a relatively crude approach. There have been a lot of studies with media transfer, where you irradiate cells and medium, and then you just take the medium and put them on top of fresh cells, with the hope that the molecules that are providing the signal are actually in the medium, and you'll see the effects in different in fresh cells. And there's also co-culturing experiments where you basically figure out ways of being able to irradiate some cells in a dish but not other cells in a dish. But certainly the most elegant and most generally useful approach is the microbeam approach, where you can guarantee that you can hit specific cells in the field and know exactly which cells they are. You can say, I hit this one, and I have not hit that, and that one. And here actually is a result of one of our very early bystander studies at Columbia. It was actually done by Charles Geard here. So what happened here is that he stained half the cells on the dish with a blue nuclear stain, and he stained the other half of the cells on the dish with a red cytoplasmic stain. And then he told the microbeam system to shoot alpha particles only at the blue nuclei and not shoot at anything else. So these cells then would have been hit by an alpha particle, but we can guarantee that these cells would not have been hit. And then he can look for the fraction of micronuclei in the blue cells and also the red cells. And this is what he got. Controls this percentage. In the blue hit cells, 30% had micronuclei. But in the non-hit cells, you didn't have as many, but you had 5% of the non-hit cells had micronuclei, and there's an example right here. So definitely more than controls, and definitely less than the directly hit cells. So this is a classic bystander response. You're seeing an increased response in cells which were not directly themselves hit by radiation. And there are various ways that you can do bystander effects. You can do, I think what I alluded to a little bit earlier, you can hit predetermined fractions of cells. You can tell a computer hit 20% of all the cells on the dish with, shall we say, one alpha particle. And you saw actually this experiment earlier. So 20%, 100% hit, 20% hit, 10% hit. So again, you can tell the computer to automatically set up the microbeam to do this. And here's another a result of an experiment with that sort of experimental design, oncogenic transformation, where here we're putting with the white curves where all the cells are being hit by alpha particles. So here every cell is being hit by one alpha particle, and the white triangle here, every cell is being hit by two alpha particles, by 4 or by 8. But the yellow curves done with the microbeam, only 10% of the cells are being hit, either with 1, 2, 4 or 8 alpha particles. And what you see is two remarkably similar data sets, the white and the yellow. In other words, it doesn't seem to make that much difference whether you irradiate all the cells on a dish or only 10% of the cells on a dish. The results are pretty close to each other, which again is a pretty extraordinary result and certainly points to bystander responses. Then another approach to bystander studies with the microbeam is to blast the heck out of a few cells. So let's put 20 alpha particles through this cell so we know for sure that it's dead. Let's put 20 alpha particles through this cell, we know for sure it's dead. But then we're going to look at the remaining cells. So yeah, the mutations observed have to come from the unhit bystander cells. So on the dish you'd either have cells which you know are dead, or you know have not been hit by radiation at all. So any mutations that you see have to have come from these unhit cells, and presumably these hit cells will have been sending out bystander signals to the unhit cells. And here's an example of some results from Tom High's group with that sort of experimental design. Here's the control population, number 1, and here 20% of the cells on the dish have been hit with 20 alpha particles, so they're dead. They're not contributing to this mutation frequency. So this mutation frequency is coming from the remaining 80% of the cells on the dish which were not hit at all by radiation, and yet show an increased mutation rate. Where we've been going ourselves with bystander studies in recent years is to 3D, to three-dimensional tissues. And I think that makes a lot of sense, because it's clear that bystander effects are due to cell-to-cell communication. So if you're interested in cell-to-cell communication, you'd better do that in some sort of tissue-type material rather than in individual cells on dishes, which have artificial connections between them. So we've done a lot of experiments, for example, in some artificial skin systems, like you see here. So I think it makes a lot more sense than the classic single cells on a dish studies look at three-dimensional tissue, this being an example. So there are various types of, we've put a lot of work into various different types of three-dimensional tissue studies that we can use, and this is just one example using artificial three-dimensional skin. You can get a skin which just mimics the epidermis, or you can get an artificial skin model which mimics both the epidermis and the dermis, and you can do studies on both of these. And here, again, here's the sorts of experimental designs that you can do, just one of many. So here's a little sliver of 3D tissue, 8 millimeters across. We can microbeam across one plane, across one diameter of this piece of 3D tissue. So irradiation only in this individual plane here. All the rest of the tissue has received no irradiation. Then we can section the tissue. So there'll be one section which did get irradiation, and all these subsequent sections will not have been irradiated, but they will be at different distances from the irradiated plane here. So we can separately analyze all these slices of tissue which are further and further away from the irradiated tissue, and themselves are unirradiated. And here's some typical examples for a couple of endpoints, apoptosis and micronuclei. So what's plotted here is the effect, frequency of apoptotic cells here, as a function of distance from the irradiated cells in microns. So this is control, where you simply just don't turn on the machine. And here are bystander responses. So these are cells, none of which were directly irradiated, but were at further and further distances away from the irradiated cells. And look at these distances. Here's 1,000 microns. So what you can see is that the effect of this particular bystander response, the range of this particular bystander response is roughly 1,000 microns, which is a millimeter, or 50, somewhere between 50 and 100 cells from the irradiated cells to where the effect ends. And the same you can see pretty well for micronuclei as an endpoint. Again, well, up to about 700 microns here, you can see a significant increase in effect when you're irradiating cells some distance away. Another example with a molecular endpoint here. This is phosphorylation of p53 at a given location, Brian Panaya's work. So we're irradiating just this region right here, and then we're looking at distances far away from the irradiated plane at phosphorylation of p53. And the black points here are in control tissue, and the red points are in this partially irradiated tissue, where the only irradiation is right here. And you can see that the red points are higher than the black points in general, even 1,000 micrometers, that should be, away from the irradiated region. Okay, well, let's talk about the mechanisms underlying bystander effects. Well. Yeah, we seem to have a little technical problem here, and the bottom line is we don't really know what the mechanisms are, and it's something that we certainly have a lot of clues, and we at Columbia and many other groups worldwide working very hard and trying to really unfold what all the mechanisms are. I think we know we have some clues as to the basic ideas, but the microbeam really is a great tool for being able to test different hypotheses about mechanisms. A little bit of history of single cell microbeams. They were first actually mooted back in the 1950s by Zirkel. But the first really practical microbeams started in the early 90s, and we can chart their growth by this set of workshops, which basically have been every 2 years, international workshops on microbeam probes of cellular radiation response, basically every 2 years, and really most of the players in the field have come to this meeting. And I've put here how many microbeams were actually represented at these different meetings. From the first one in London in 1993, one of these three was Columbia, to the last one in Darmstadt in 2010, and the next one upcoming in the spring of next year in New York, to which I hope you'll all come, is the 2012 10th meeting. And you see a solid increase in the number of microbeams as a function of time. Exponential increase, perhaps slowing a little bit now, but yeah, they're certainly approaching 40 microbeams worldwide at this point. Here's a list actually that I put together in 2006, so it's out of date. I can add just a few extra ones here. So there's various parameters: low LET, high LET. Are they X-ray microbeams? Are they charged particle microbeams? Are they both? Are they online? And also, very relevantly, can they actually do biology? Because it's one thing to get a microbeam online, to actually get the biology working, as you'll see over the next few days, well, that's a whole other kettle of fish, much, much harder. If you want to do experiments with live cells, of course they have to be outside the vacuum of the microbeam, and that's one of the big issues with microbeam studies in the biological world. So I think I'm going to end there with that very brief introduction. I hope you'll see that the RARAF microbeam is very biologist friendly. We are really here to serve the community, both within Columbia and outside Columbia in the US, but also worldwide, for probing intracellular and intercellular communication. And I'll just flash up all the people that you're going to be seeing in the next couple of days, and I think getting lectures from many of these folks. This is the Columbia Microbeam team. And again, thank you.